visualization platform. So the pilot is a nutshell. We have data sources from ground-based satellite volcanic observatories and models, and database. So at the database level, we need to homogenize the data to transform them in the suitable format, to exchange data between the different components of the system, and to archive and transfer them. And then we have the visualization platform, where we will show the 4D distribution of the volcanic plume, and this is important for the dissemination of the forecast end of the product. And so this is the last part, which is mainly devoted to the users. So let's go through an example, which is also the object of an exercise that we are going to have into the demo. So we have the Etna eruption in March. Etna erupted many times during last winter and spring, and we selected the case for 12th of March because we have a big lava fontaine and ash transported far away. So we have the eruption, then we have at the observatory, the VONA, which is the volcanic observation notification for aviation. So with main basic information which are needed for the aviation hazard and which are collected from the VAC. At the volcanic observatory, we have also the identification through the camera and of the altitude of the plume. So this is a basic tool and example of that. And this is really an important information. Then we have still from INGView, from the surveillance system, the looking to the 3D images for getting information about the clouds and the ash. Sorry. And for showing you, these two pins are the location of some in situ atmospheric observatory in Antikythera and in Cyprus. And these two sites are part of ACTRIS. ACTRIS is a research infrastructure for aerosol cloud and trace gases study over Europe. And here I show you the information about the temporal evolution of the aerosol fields over Antikythera and Limassol. On the x-axis, we have the time, and in the vertical, there is the vertical layering. And so you can see some feature here. The red stands for intense aerosol layers. So we have a layer identified over Antikythera in Greece at this time on 12th of March, and on 13 the plume reached Limassol, so in the east, more in the east, and in the early morning. And on this kind of data, we can apply some methodology which are tailored for the aviation, and I will show you later better, for identify the volcanic ash. This is a model situation, a simulation instead. So with the forecast of the plume made by NOAA, and where you can see the ash plume moving toward Antikythera. All this information are interesting and are produced in an independent way and are really to be integrated into our pilots. And for doing that, we went to the user for understanding the requirement for the end product. So there were some communication with the user community. So first of all, we had a one-to-one discussion. So direct contact with interested people and potential user, but also the E-Shape community of this pilot attended some meetings of the user community for having the feeling of what they need and understanding that. And also we have some heritage from previous initiative and projects, like UNADIC's AV Horizon 2020 project, but also other initiatives as the VASAG into WMO initiative. And the lesson learned about this, first of all, we understood that no specialized community, so let me say no scientific community, have a different needs in terms of visualization of the product, and also the use of a different vocabulary that we typically use a very specific and scientific vocabulary, and this is not suitable for end user community. And also we saw that different communities may need different tools, and also different needs are to be addressed for them. Some important point is that, for example, our color maps are typically not really efficient because we have a degradation of the colors and different colors there, while instead something like, yes, there is an hazard, no, there is no hazard, color map very easy to be understood, are much more efficient. And also that for a community like VAC or CSR, a one unique place where all the relevant information are collected is much better than having a sparse website and repository for the different data. And also important is that an appealing and professional visualization tool is a key message for the users. So they want to have something which looks like professional. So replying to these needs, we had some tailored products. This is one example for satellites. So having the MODIS images showing the plume, then there is, it was developed a tailored product that just provide a ash, let's say, mask. So showing where the ash was detected. So with this orange pixel in the maps. And for what concerns the LiDAR, I show you, this is the particle backscatter coefficient, which is typical product for actuaries research infrastructure, and the particle depolarization, and then we have the mask. And we produced this new product, which is tailored for the aviation, in which we identified the low, medium, and high risk for the aviation. And so we moved from something which was scientific to something tailored for the aviation. So we have an aviation alert product. All of these can be also simulated, and LiDAR profiles are made available in real time, and it is done under a different contract with CAMS for 11 actuary stations, and showing the potentiality and the possibility of near real-time provision, and so in principle also simulation. And this is done at pilot level at every change in the situation in the VONA, so in the alert, and also checking for new observation every 3 hours. And in this way, the arrival of the plume for the March case of 2021 for the Etna eruption, the arrival over Cyprus were better described when a simulation is done. So also for going towards the users, we have data source database and then the visualization platform. This is one example in demo where you can see the different colors for different intensity, and then clicking on the station, you can see the LiDAR profiles with the different products. So the standard product from actuaries, but also the color code aviation risk, and also models with the different percentile, and also you can choose different levels for showing the different flight levels that also the VAC is showing into their platform. And you can zoom in, changing the time, and all these kind of things. But as I said before, it's important also to have something which looks more professional and nice. So we are going to work for having the pilot hosted on a more professional platform, which is the Adam Explorer platform from EO. And the pilot is the implementation of the pilot over there is under development, but just for showing you, what we have is a platform where you can open the different layers, and you can include the different observation there, of course, accepting the different, let's say, policy, and the showing and exploring and so on. So just for summarize, so we have the
1 minute.
Yeah. We have the visualization of state-of-the-art tailored integrated product, and also with this platform we can add troponomy from data from DIAS like troponomy, and so we'll have embedded the satellite in situ model data, also considering research infrastructure, and this is something different. It's not focused on just on one region. This is a European level, but this could be applicable at a global level. And I close and thank you for the attention.
Thank you, Lucia. We have just 2 questions. Did you collaborate on this project with other geo communities, regional or thematic?
Yeah, I mean, as I said in the last slide, this is not related just to one location. So it is already European and even open to the global. So the collaboration is, of course, embedded in it, in the design and into the realization of it. Yeah.
And so your services are extended beyond Europe?
Is not indeed already extended beyond Europe, but it's open to that because we are using the same standard of the different in situ community elsewhere, so in the other continents, and the in situ component is already linked with them because we have the same standards and also the same kind of product. So it's easy to be expanded to at a global level.
Okay, thank you very much. Just on the previous presentation, Lucas and Katerina added some links, so you could look at the discussion to find those links on the GEOSS link, and a link to the website, some information on the website for the GMPDWH Knowledge Hub. Okay, so next presentation is by Patrick Matron from the Luxembourg Institute of Science and Technology, LIST, and he will be presenting an E-shape pilot project on satellite Earth observation derived water bodies and floodwater record over Europe. Patrick, yes, I see you. The floor is yours.
Good morning. Thank you very much, Lilian, for the introduction. Wait, I will try to. Can you see my screen?
Yes, we can see your screen.
Okay, so it's a pleasure to have the opportunity to present you our E-shape pilot. I would like to start by mentioning the objectives, although they have slightly changed since the beginning of the project, and I think this is in line with the, let's say, the philosophy of E-shape, where products are developed with and for the users. So we started by aiming for the generation of the water bodies and floodwater record over Europe at 20-meter resolution using Sentinel-1 data. There were other objectives like to understand flood hazard at continental scale based on EO-derived flood maps and long-term hydrological modeling simulations, and to support our main end users that are grouped in what we call the Global Flood Partnership. So the Global Flood Partnership is a cooperation framework that brings together scientists working in the field of large-scale flood mapping and prediction, and different flood risk managers from around the world. But as you can see, we slightly deviated from these initial objectives, and this is what I will also put some emphasis on during my presentation. So where we all started. Basically, what I call here the background or background IP of the project was that in our team, we had developed several years ago a methodology to map flooded areas from a pair of radar imagery. So I have this one slide to just introduce the problem that we were facing. So when you have a radar image like the one you see here on the screen, and you then draw a histogram of the backscatter values, it's very difficult to differentiate the flooded from the non-flooded parts or the pixels that changed since the last acquisition, because the fraction of the flood is relatively small at the scale of such an image. So we have developed a hierarchical split-based approach that cuts the image into sub-images where this B-model distribution becomes visible. So by focusing on the areas that you see here in green, you can start separating the water from the no water class and the change from the no change class. And that's where E-shape basically started, because based on that technology we wanted to develop a large-scale application and process an entire archive of satellite images acquired over several years. So the chain we had developed consists in using a pair of images acquired from the same orbital track, and then to map all the pixels that have changed since the last acquisition. So you see here, for example, in blue, the areas where the water has receded, and in red, where water has appeared since the last acquisition. And you use these two classes then to update the water extent map from the previous acquisition. So you add and subtract the flooded pixels to update that map on a regular basis. So from the beginning of eShape, of course, a lot of emphasis was put on co-designing, and we benefited from experts in that domain that are part of the eShape consortium. So we started from this, let's call it the baseline product, just flood extent that is regularly updated. And we wanted to know from different user communities how this product should evolve to satisfy their needs. And we tried out two different frameworks to do this co-designing together with many different users. The first one consisted in focusing on specific areas of interest around the world and to build a sample of products, to share them with the community and to ask them to explore this data set and to fill out a survey so that we could get an overview of the needs from different user communities. I must say that this has not worked that well, because I don't know if probably some other people in this session made the same experience. When you ask people to spend some time on filling out forms, then sometimes the result is a bit frustrating. So we did not get that much feedback from our users. But then we were lucky because the chair of the Global Flood Partnership is the Joint Research Center. And the Joint Research Center, they are also in charge of one of the Copernicus services, in particular, namely the Copernicus Emergency Management Service. So the CEMS provides disaster management information free of charge based on space data combined with other information. And it aims at supporting all phases of disaster risk management, so the preparedness phase, the emergency response, and the recovery. So they were the, let's say, the ideal user for us to see how a systematic automated flood monitoring service based on Sentinel-1 imagery could complement this system that they have, or monitoring system they currently have. And the JRC invited us to be part of an expert team that they had put together a couple of years ago to study the feasibility of an automated global satellite-based flood monitoring product to support their service. And from these exchanges we had with the JRC and many of the users they are working with, showed that there are some significant limitations of the CEMS at the moment. So there's no constant automatic monitoring of flood extent at global scale. Every time there's a major event somewhere in the world, somebody has to require or trigger the satellite image acquisitions or require the processing of this imagery. Often it happens that the peak of the flood is already passed when the activation is launched, and there's currently no possibility to map all floods in the world. So their requirements was that we need to have such a systematic continuous monitoring that would not require any triggering effort from any user. Also, they required to drastically shorten the latency between the acquisition and the product dissemination. Also, they required access to historic data that would help them in their prevention planning. And to satisfy the needs from many different users, they also wanted the access to be as diverse as possible. They also clearly told us that our baseline product, the observed flood extent, only partially meets their needs. So they asked for other products that should complement this baseline product. One is the reference water mask, so the permanent water bodies and seasonal water bodies. They wanted to have an idea of the ensemble uncertainty, so the classification uncertainty. They want us to put advisory flags, so in case you have classification errors due to snow, ice, frost, dry soils, and wind. Also to add an exclusion layer that should inform on all areas where the retrieval of flooded areas is currently not possible using SAR data. And they wanted to have information on the impacts, like what are different land classes that are affected by a flood, what is the number of persons affected by the floods. And all this together with some Sentinel-1 metadata, like the footprint that was observed, the scheduling plan, so when the next acquisition would take place. And all this information should be available just 12 hours after the data acquisition. So that was what we spent most of our time on during the eShape project. So we starting from this the software or this method that we had developed and that I showed you before, we had to first of all refine this method so that it could be adapted at a large scale. So there are significant challenges because of what we call water lookalikes. So for example, wet snow, dry land, vegetation. So these are areas or ambiguities need to be clearly identified. Also, we needed to develop a processing chain to generate all these other products they were requesting, like, for example, the exclusion layer. So based on time series analysis of SAR data, we had to identify what we call blind spots, so areas where no classification can be achieved. In addition to that, we had to put some effort on the efficiency of our workflows to meet this criterion of 12 hours production latency. And that's when we started working directly with the Joint Research Center on the provision of an automated global satellite-based flood monitoring product. And that's when also other partners came into play that were not part of the initial eShape proposal, but were part of this larger effort of setting up this system for CEMS. But I put here powered by eShape because the core of this service is, in my opinion, the retrieval algorithm that was developed within eShape. In the final service that I'm going to show you just in a minute, there are 3 algorithms that are used for the mapping of the flood extent on a regular basis. So there's our eShape algorithm that is based on the detection of changes between 2 subsequent image acquisitions. And we have also an algorithm from the DLR in the loop that maps all flood water using just one image. And there is a third algorithm from the TU Vienna that is based on time series analysis. So they look at an entire stack of images and do a time series analysis of backscatter over time to decide if a pixel on a given date is flooded or not. So in the end of this service, we have an ensemble algorithm. So we look at the classifications achieved with these 3 algorithms, and then based on the majority decision, we classify a pixel as flooded or not. Here you see the entire workflow. So I put here in red all the components of the system that are directly related to eShape. So there's the algorithm that we at our institute have developed, plus the design of all these other products that the system should output on a regular basis. So this system should be applied to process around 1,000 Sentinel-1 scenes that are acquired every day, and to produce the 11 output layers requested by the CEMS managers and their users. The chain uses as main input the Sentinel-1 data sets, but 12 auxiliary data sets are also needed in the chain to improve the robustness and reliability of the products that we are generating. To be frank, I'm not an expert myself in the IT infrastructure that is used for providing this service. I just wanted to show you that that we had to collaborate with IT experts to implement our algorithms on their processing platforms and to ensure that there's also fast access to the satellite imagery. So there are different components in this IT infrastructure. There's the processing layer. There's then the data and metadata interface, plus a layer that is dedicated to the product dissemination, because as I mentioned before, the JRC requests us that the access to the data sets is facilitated and available for many users from around the world with their specific requirements. And of course, we also had to make sure that the product and the service is regularly evaluated so that the quality can be assured. I put just one slide on the product dissemination. I think that the CEMS, of course, is very much in line with the philosophy of GEO, as the purpose is to provide free access to all the GFMS products for users from all around the world. we adopted a RESTful API to make it sure to integrate the data directly into the working environments of the different users. We have also set up a web application for the visualization of all the products, and we make sure that all the OGC standards are followed to access the output layers. So I want to finish. Sorry.
So you have 1 minute left.
Okay, perfect. Thank you. So we started the pre-operations on the 12th of September. So I can make a very short demo, but it's not comparable to what my colleagues now showed you before, since the system is just still very much in development. So you see here a screenshot of all the Sentinel-1 images that were acquired yesterday and that were processed by our software. We are busy now finalizing this system, making sure that the products meet the accuracy request or criteria from the JSC, and it's planned to launch the system on the 25th of October. I want just to briefly show you where we are now. So this is not a very, maybe not a very interesting page to show you, but it's the API that should ensure the fast access to all the data for the end users. Here at the end, maybe it's the tool that is of most interest. So you have a search tool where the user can specify its area of interest, the acquisition date, and the products it is interested in, and it can then directly download the data that was generated. So you see here the file path where the corresponding products can be retrieved from. And to make it even easier for the end users to have a look at all the images that are currently available, we're in the process of setting up a GEOSS server, where you can see here the world map with in red the areas where in the last 24 hours some anomaly was detected. So when you zoom in, you can then detect the flooded areas that are, okay, here it's a very small anomaly, that give you an overview of the flood extent from the last days. So in the end, there will be an access to a full catalog from where the user can select the data he's interested in and retrieve then the final product. I think I will not have time now to spend much more time on the evaluation that we did over the last months over the different test areas. Just to tell you that we have selected different areas around the world to measure the accuracy of the classification that was obtained. And one message here was that actually the most challenging issue is to process images where there are no floods because of all these ambiguities that I had mentioned to you before, and we are still working on this to reduce the uncertainties of our classification. And that's all from me. So thanks a lot for your attention.
Thank you, Patrick. We have just one question from the floor. Do you use GRDH data? And if yes, why not 10-meter resolution, which is native for those kinds of data?
Yes, we use GRD data. That's right. That was a big discussion actually, if we should take use the products at the 10-meter resolution or 20-meter resolution. I must say I don't remember exactly the argument that was used finally for 20-meter. So there's of course the reason of the data that can be, or the storage requirements that are significantly reduced by working at 20-meter resolution. And I think the main argument was that the initial product is at 20-meter resolution and is then resampled to 10-meter resolution, which is then, but the initial resolution is 20 meters. So there are some scientists in the team that argued that there's no added value in going for the 10-meter resolution, but there is the constraint of having much more data to store and to process.
Sorry, can you hear me? Did you
Yes.
also go off, or did we just disappear?
Are you talking to me?
Yes, Patrick, sorry,
yes.
I think I had a little connection issue. Have you finished answering the question?
Yes, I hope that some people heard it.
Okay, sorry for that. Okay, before we go on to our next presentation, I think Audrey, you wanted to say something?
Yes, I will. We're just going to take a 5 minutes break because we're having some technical issues with the two next speakers from CLS because they don't have access to the desktop-based Zoom. So we're just going to try and see if I can share their slides, and we'll do that. Anyways, I've added to the chat box the link to the PowerPoint. So I will be giving a restitution to the plenary session right after this breakout room. So please have a look if you haven't done so. Also, I would like you all to stay for the plenary session after this breakout session, because if there are some questions asked about your project, I will obviously not be able to answer them correctly. So make sure you stick around for this. So we will take. I will say, okay, we will come back at 10:15, so everyone has time to take some coffee, and we'll get the next two speakers up and ready for you when you get back. So talk to you in 10 minutes. Thank you all.
Bonjour, c'est... Hello, Claire.
Hi.
Oh, there they are.
Okay,
Bon,
so
désolée, c'est vraiment très compliqué là ce matin. Pourtant, ça marche bien d'habitude, mais là, impossible de passer sur les sessions partagées, la parallèle, c'est bizarre.
ok, donc...
Bonjour, avez-vous considéré d'installer, si il y a des problèmes d'utilisation de Zoom, de l'installer sur un smartphone et de se connecter alors directement avec le smartphone?
Bah, je suis comme ça, ouais. Je suis connectée avec mon smartphone, mais du coup, pour faire une démo et partager mes slides, là, c'est un peu compliqué.
Ok, bah du coup, je vais prendre la main et je vais partager vos slides.
Ouais, je veux bien, ouais.
Ok. Alors, attendez, je les ai déjà ouvertes. Ouais, elles sont là. Je vais partager mon écran. C'est vrai que pour la démo, je ne vais pas pouvoir...
Non, après Marion sur SamTool, elle a déjà fait pas mal de présentations quand elle a, et donc elle sait le faire. Elle a des, pardon, elle sait le faire. Elle a des screenshots dispo. Moi sur l'Ethoscope, j'avais pas prévu de backup en fait, donc j'avais juste prévu de parcourir le site web, enfin, la plateforme et tout ça. Et là, je vais pas avoir le temps de préparer quoi que ce soit.
Est-ce que ça vaut le coup que j'essaye de partager la plateforme?
Et que je t'explique comment on va perdre du temps, enfin, parce qu'il faut que je t'explique, va sur ce truc-là. Elle n'est pas très grosse, hein, elle est beaucoup plus simple que SamTool, mais...
On peut toujours essayer, mais du moins, je pense que ce serait bien que tu m'envoies le lien, comme ça je peux le partager dans le chat.
Ouais, alors après, elle est authentifiée, hein, c'est quelque chose que j'explique dans le... Là,
Ah
sur
oui.
ce page-là. Donc moi, pour toi, je peux te donner les accès, il n'y a pas de souci.
Oui, c'est plus compliqué,
Mais
effectivement.
voilà, tu ne le partages pas.
Oui, donc c'est pas la peine de partager le lien. Okay.
Non,
et là, sur cette slide, par exemple, là,
on voit un exemple. Je peux essayer de le commenter. Effectivement, je zoome un peu. C'est bien, je peux zoomer avec mon truc. Sauf que c'est en français. Là, moi, je l'avais loadé parce qu'on peut le mettre en version anglaise. Et donc, je l'avais... je l'ai pas préparé, mais moi, sur mon web browser, j'avais préparé en version anglaise.
Ouais.
Mais après, je peux te l'envoyer si tu te le sens, Audrey. C'est toi qui me dis.
Bah, vas-y, je peux toujours essayer. Hein.
Ok, je te l'envoie pour l'instant. Et tu fais le test pour Marion. Je ne sais pas si Marion nous a rejoint.
Si, je suis là. Vous m'entendez?
Oui, on t'entend bien, Marion. Et du coup, j'ai les deux je crois que c'est Claire qui commençait et ensuite Marion. Ouais. Et ouais, j'ai vos deux présentations là. Donc,
moi, je suis en train de faire quelques screenshots là pour te renvoyer 2-3 slides en plus qui serviront de démo.
D'accord, ok. Donc, tu feras ça pendant qu'on fait la présentation avec Claire.
Ouais, j'en mets une dernière là et en fait, je te renvoie une version, une V3.
Ok, bah, je vais fermer ça du coup pour pas...
Voilà, ce sera juste pour montrer un peu, ce sera moins dynamique, mais bon, ça change.
Oui, c'est déjà ça, quoi.
Voilà.
Tu aurais dit à quelle heure? À 15 hein?
Ouais. Voilà. Allez, hop, une dernière. Je te l'ai envoyé, Audrey, le mail, si tu veux essayer de jeter un œil.
Je suis en train de l'ouvrir, Marion. Non, Claire, pardon. Claire?
Oui.
Est-elle de retour? Oui. Ça y est, je suis connectée. Je vais partager mon écran.
Ouais.
Tu le vois?
Ouais, je le vois.
OK.
Du coup, est-ce que tu peux aller sur la map monde en haut à gauche, cliquer une fois?
Hop, pardon, ça a cliqué 2 fois, super. Ah non.
Il faudrait que tu aies fixé avec la petite épingle, voilà, c'est ce qui pourrait éviter ça. En fait, il faut que tu réappliques sur données géographiques, tu fixes avec la petite épingle
Hop.
pour laisser le menu, voilà.
Ouais, super.
Bon, du coup, tout est en français, donc je sais pas, bon, ça aurait été bien si tu pouvais passer tes settings de browser en anglais et le reloader.
Les settings de browser en anglais et reloader.
Ouais, donc c'est sur quoi là? T'es sous... C'est Edge, hein?
Je suis sous, non, pas Firefox.
Ouais, je connais pas. Du coup, il faut que tu fasses préférence de langage. Je sais pas, c'est paramètres. Ouais.
On va trouver, on va trouver.
Hmm.
Sachant que c'est ma bataille perpétuelle de tout mettre en anglais et les informaticiens sont pas toujours.
Langue,
Là,
la
ça y est.
langue. Ouais.
Je suis pas sûre d'avoir, tu vois, l'option d'auto.
Ah,
C'est un peu mon
bon.
problème.
Bon, écoute, c'est pas grave, sinon.
Oui.
Je vais te
Je
montrer.
traduirais en temps réel.
Ouais, bon, c'est pas très. Enfin, je dirais aussi. C'est juste que ça va prendre un peu plus longtemps. J'avais pas prévu de passer 10 minutes sur la démo, tu vois, mais bon. Ah, si, super.
Je pense que c'est pas mal. OK. Ça dit please wait, donc c'est déjà pas mal. Je vais repartager mon écran du coup. Où est-ce qu'il est? Il est là, lithoscope. Et nous sommes en anglais.
Yes.
Incredible.
Voilà, donc du coup, tu peux cliquer directement sur, par exemple, une des deux zones, la zone dans Méditerranée ou celle que tu veux. Là, tu peux zoomer, enfin, tu peux descendre, enfin, tu peux cliquer sur la carte, sur l'AT, là, par exemple, et scroller pour faire bouger les couches d'information dessous, là. Tu peux fermer ça, c'est de l'information, mais après, tu peux, voilà. Et là, tu peux zoomer avec en roulant ta molette, là, et tu peux faire bouger ta carte en cliquant sur la souris, puis en la déplaçant, comme Google Maps, en fait.
D'accord, ok.
Voilà.
Oui, c'est un peu lent, je pense, avec le partage Zoom.
Ouais, après, c'est effectivement, normalement, enfin, souvent, c'est plus rapide quand on précharge les layers. Mais
Bien sûr, ouais.
la zone la plus compliquée, celle-là, parce qu'elle est, c'est pour ça que je t'ai fait choisir celle-là, elle est plus grosse.
Ah
Et
bah
après,
attends,
si
je vais
tu
choisir l'autre.
bah, écoute, si tu me dis que c'est, ouais, moi, ça va.
Hop.
Yeah.
Ah mince,
Après,
je peux plus.
tu reviens, en fait, tu cliques sur Coastal Flooding. Et tu peux choisir ta étampe à la... Ah, c'est en français, ça. Ouais. Étampe à lavassien là-haut. Tu peux cliquer sur la petite flèche qui va vers le bas et là, tu choisis la ville de Gap.
Ok, ah oui, c'est plus simple.
Ça doit être beaucoup plus léger.
Ok, bah on va reprendre la session. We're going to start again. I will give back the floor to Lilian.
C'est OK parce que j'ai du bruit derrière dans la maison. Est-ce que vous l'entendez ou pas?
Absolument pas.
No.
OK. Parfait.
Okay, so I hope everybody's back. Sorry for that technical error. So our next presentation will be by Claire Dufault, and Audrey is going to have to share her screen because Claire cannot. And so Claire Dufault is from Localisation Satellite, CLS, France, and she'll be presenting the Litoscope project, which is a satellite solution identifying flooding risks in coastal areas. Claire and Audrey, are you ready?
Yes, thank you. So I just opening my camera just for saying hello, but I will stop sharing it because I need some bandwidth here on the phone. So thank you. So my presentation today is to talk about the Litoscope project. So it's a project we conducted in partnership with the French Space Agency and also the National Geological Risk Institute, BRGM in France. This is a project which is embedded into the Space Climate Observatory Initiative, which was launched in 2017 and signed 2 years after by more than 20 space agencies. And Litoscope is one of the first flagship projects that was launched last year, and it was a one-year project, and it means that we have just finished it. You can go to the next slide, Audrey, please. So the project Litoscope deals with developing a satellite-based solution to estimate and inform decision makers about the risk of future coastal flooding due to the sea level rise and also extreme events on top of this sea level rise. For doing that, we have combined two families of satellite observation. The first one is the altimetry, which monitors the sea level from for the last 30 years. And we combine it with the very high resolution optical imagery, which monitor the coastal territories, the digital elevation, the land use. So we use these two technologies to develop a replicable tool in order to help in the guidance of the local decision, in order to provide the better knowledge regarding the risk. So the tool is dedicated and was dedicated to the coastal territories, and we have for that involved two French territories as demonstration area to collect their needs and to co-design with them the risk indicator and the way to disseminate them through a web portal. And I will present you today the results of this development. So you can go to the next slide, please. So technically speaking, the optical imageries have been used to extract first digital elevation model onto the two demonstration areas. The accuracy of this digital elevation model was assessed by a comparison to existing LiDAR digital elevation model. That's why we selected these two territories for demonstration in order to make a comparison and evaluation of the capability of using satellite-derived digital elevation model. We get, so for the first area, which is on the Atlantic side, we get a bias of 20 centimeter and a less, so you can go to the next slide, Audrey, please. And a reduced bias of 5 centimeter in the other. The standard deviation, so the vertical accuracy for these two digital elevation model was respectively of 1 meter and 60 centimeter, which correspond finally to the expected vertical accuracy for such digital elevation estimation from satellite Pleiad images. Regarding the spatial resolution, the two digital elevation models were estimated at 50 centimeter, especially. You can go to the next slide, please. On one area, so on the Atlantic side, this satellite estimated digital elevation model was tested in a high-resolution hydrodynamic modeling chain already developed by the BRGM to reproduce a 2008 event. So they replace the initial LiDAR digital elevation model by the satellite-derived one to estimate the impact. So you have on the left the result get with a LiDAR solution, and on the right the flooding gets from the satellite digital elevation model. So what we obtain is that there is a limitation of the current accuracy of such area where the wave overtopping is very important, and where we need high resolution modeling, we get an overestimation of the flooding for the moment. But we have identified some improvement in the data processing of the satellite imagery, and we also expect to improve this vertical accuracy thanks to new satellite mission coming in the next decade. You can go to the next slide, please. Besides this high resolution modeling exercise, we applied also a static approach, which is as a first start a very good starting point to evaluate the coastal hazards and by comparing simply finally the land elevation height with the several scenarios of water level at the coast in the future. So the 24 scenario we considered took into account first the sea level rise observed with altimetry in the past 30 years, so coming from the Copernicus Climate Service and Marine Service. But we also used two climate models from the IPCC group in order to take into account also the projection of this gas emission in the future. On top of that, we also had the effect of decadal storm surges, so taking into account the atmospheric pressure and wind effect and the tide to the sea level rise itself. We used value coming from global model, so the first 2014 and to go for this evaluation. You can go to the next slide, please. We also use the very high resolution optical imagery to map the socio-economic stakes over each territories. So the land use, as you have here on this slide, but also on the next slide, we compute the distribution of the population over the small city, so on the Atlantic side, at building level. So it was done using both the economic, so the land use distribution, but also the knowledge on the building thanks to the digital elevation exercise. Next slide, please. On top of this hazard estimation and stake estimation, we have made an evaluation of the risks themselves generated on each coastal territories. And for that, we have considered 5 types of exposure. You have them on the slide. So as I said, some of them have been fed with information coming from the optical imagery, so the land cover, the population, And the other information came from local, national databases. Next slide, please. For each scenario, we got a panel of information like this one you have in front of you. So the hazard itself on the top left, and then the 5 different risk estimation. We estimate the hazard on hexagon of 10 meters. Even if we add a digital elevation method of less than 1 meter, we decided to keep medium resolution regarding this high resolution provided by the images themselves, in order to take into account the fact that we just applied a static computation. We are not doing hydrodynamic modeling. And for the risk itself, as we cross the hazards with lower resolution layer, we kept a 30-meter hexagon resolution. You can go to the next slide, please. To disseminate all this information towards the coastal manager and elected people, to help them getting familiar with the hazard and also discussing with the territories and taking decisions, we involve them from the beginning. So because we would like to design and to build a dedicated interactive web portal with them. So we met them several times at the beginning of the project. And it was not an easy task because we were in the COVID-19 situation. So, but we managed to meet them also physically, and to have such discussion is quite important at the beginning. And so we have designed and built a portal that have been tested and evaluated by several groups of coastal managers. And I will detail the feedback we get and we gather from them. But maybe before that, we will try with Audrey a small demo.
Yes, we can definitely try this. I will share my screen again to get on the. Okay.
So it's an uncertified platform, so you need to have a password to access the information. But when you click on, so you arrive and you see the 2 areas which have been studied. So if you click on one of them, you start by having access to the hazard layer, so you can zoom in. So it's for the total submersion, so combining the sea level rise and the decadal storm effect. If you click on the permanent submersion box, Audrey, just below the total submersion, above, you have the result for the permanent long-term submersion. So you see here in GAV is very, very few impact. But you can, it's for the year 2030, so you can go in the time scale on the left, and you can click, to change. So let maybe the time for the browser to load, and you can go, until 2100. And you can change also, this is a result for the satellite observation from the last 30 years. If you choose the first scenario or the last one of the IPCC, you can see that the hazard is changing. Okay, you can zoom in a little bit. And then you can go into the risk estimation. So you can click on the human risk category. So so very few risk for this scenario, and you can choose the socio-economic, environmental risk, heritage risk, and so on. You can change the color bar, but I will not explain you today. I think you can. I think it's so all the layer has been loaded and can be displayed. Something that I've not explained, which is hidden here. You have an explanation. There is an E box, which is below the latitude longitude value. So here for explaining the lithoscope project, but you have also below the 43 dots. So there is something with a high.
Here.
Yeah. And you have an explanation of how this risk have been computed, and for each layer you are displaying, you see the explanation, because we need to explain very clearly what have been computed and how we reach this value, because it's very crucial to risk manager to know exactly what there is behind, not just giving value, but explaining how we get it. So here we are. I think we can come back to the presentation for the final slide.
Yes. Okay. So I need to go back to.
Thank you, Audrey. It was very good.
Thank you. I must say it's good. It's good to show everyone that the platform is very easy to use.
So final slide. So the user feedback we got from this period of trial on their side, they say that they are really interested in the map produced. They increase their knowledge about risk, even if they know that the methodology is limited, and also that satellite approach is sometimes less accurate as a LiDAR measurement, but in some place where we don't have any information, it's already a first very interesting information that we can get easily with satellite. They also find the web tool useful for future dialogue locally. So they envisage to keep it in their meeting with the manager, between the manager and elected people. They appreciate the design and the ergonomy of the tool, and they also appreciate the identify access because they need to control the dissemination of this sensitive information about risk. Because you can imagine that people living there want to make some decision also in terms of buying, selling houses. So I think it's really very sensitive information. We also identify several evolutions that could be implemented, maybe to do something, the educational content, so the box for explaining what we have compute, more accessible and complete. So they need more detail, much more detail that we did. They also need maybe a simpler access to the button, information button and the tooltips. So it's something to be pushed forward in terms of ergonomy. And also maybe better highlight the data units and within the color bar, which is quite small for the moment. And they also appreciate to have a clear warning on the limits and the application scale of the results. So here we are. So we can say today we have developed a replicable tool. So this is scalable for other coastal territories. This is the strength of the satellite approach. We know that there is some limitation, but we clearly think that we can now go outside the territories that are already well studied and try to push this methodology elsewhere. Thank you for your attention. I'm stop here.
Thank you, Claire, for your presentation. We do not have any questions, so we will go straight to the next presentation by Marion. Oh, there's a question? Sorry about that. There's a question. Claire, what about the accessibility of the presentations? Oh, sorry. That's for us. That's for us. So I think there will be, I'm not sure if the presentations will be made available after this meeting.
I'm not sure. I think we can get this information from Jean, but yeah,
yes,
I'm not aware of
it. Thank you for the questions. All the presentation will be uploaded on the website of the event, but that will take a few days before we do it.
Okay, so let's move on to our next presentation by Marion Sutton. She's from CLS France, and she'll be presenting an E-shape pilot on sargassum detection for operational seasonal flooding, the SAM tool. Audrey, will you be sharing your screen again? Yeah?
Yes.
Okay. The floor is yours.
Thank you.
Yeah.
Hello, good morning, everyone. And thank you, Audrey, to help me on this presentation again. So my name is Marion Sutton. I'm working at CLS, and I'm in charge of this Sargassum activity that we have been developing and working on for a few years now. So I will present what we've been doing and the process that we've done following a great co-design approach. I will remove my camera as well and continue sharing. Okay, thank you. So just to give you a bit of context that you may probably know already, the Sargassum influxes have been impacting the Caribbean and the African coasts for more than 10 years now. So since 2011, we actually started to see Sargassum strandings occurring on the Caribbean coast and on the African region. There are still a lot of research going on this subject. A lot of laboratory in the US, in France, in Mexico, and elsewhere are working on this subject to understand what is happening with the Sargassum and why do we have Sargassum arriving now that we didn't have really before. The latest hypotheses are talking about strong anomaly in the current circulation back in 2009, 2010, that had allowed the Sargassum that were already existing in the Sargasso Sea for decades. And in this winter, the change in circulation has probably allowed the Sargassum to go out of the Sargasso Sea and then to be drifted in the northern Atlantic circulation. And you can see on this map here that from now, the Sargassum started to find a new area for their proliferation and life, and a good area for them. And then they've started to proliferate, and then to cyclically go to the West Africa and the Caribbean region and strand on this area. And the yellow area that you can see here is actually what we call the new Sargasso area. Sorry. Next slide, please. So now that we know that there is Sargassum at sea, but the problem is that it actually has a lot of important impact on coastal and maritime activities. So public authorities have to clean the beaches because it has an impact on health, on the health of the people. It has an impact on the tourism sector as well, because tourism is a key resource, is a key source of revenue for most countries in the Caribbean. It has an impact on fisheries. When fishermen are prevented from going offshore and going to fish because they are trapped in the Sargassum on the ports. It also have impact on operation and security at sea, and also in the wildlife protection. So all these impacts are very important, and we've decided to see what we could do with the use of satellite data to actually find a solution. So next slide, please, Audrey. So in this frame, we decided to develop the SAM tool project, and this was our answer to raise awareness on the upcoming Sargassum strandings. It was also to help the users to prepare in advance mitigation plan to reduce the economical effects, and to prepare and support the timely and costly collection operation at sea or on the beaches. So for this, we developed the service with a strong community of users. And next slide, please. And the design was actually done in several phases. So we started in 2018 with the support of the ESA by refining the end users requirement through answer-oriented questionnaires. So we we asked the people, local population, to understand what they really wanted to access as information and what was their need, what they were using before this new service. Then in the second phase, after the first development of a prototype, we provided a 2 months user trial, and we got feedback questionnaires from these people, from the user that had been trying the system. Then we entered a second phase of collecting the feedback and improving the system. And we entered a second phase of trial that lasted for 7 months. So this was in 2020, again with the support of the ESA. And while we initially had a wide range of users in a lot of different activity domains, from university to operational user, security, environmental agencies. In the phase 3, we decided to focus on one particular category of users, who was operational users. And this is because while refining our tool and discussing with the users, we realized that it was very difficult to answer the needs of a wide range of users that had really different needs. So we decided to focus on the operational needs and to develop the SAM tool to be an operational system for operational mitigation plans. Then the last phase that we've started in 2020, and this was in the support and in the frame of the eShape project. We continued our co-design approach, but we entered discussions with what we call ambassador users. So this is a term that means that it's not only an intermediate users that will redirect the service to end users, but it's more like an ambassador, because it also helps to valorize the system that we are developing to other users. So this ambassador users is the CERMES, who is based in Barbados, and is really using our data, what we are producing, to valorize and to produce their own service to the end users, to their community. Next slide, please. So now that I've explained what was the approach, what is the SAM tool service actually? So it's a warning system for sargassum influx. So this is based on using 6 satellite sensors. So we are really valorizing the Earth observation data, and in particular optical sensors. So we have using European and American optical sensors to detect the sargassum from the space. And with this detection, on a daily basis, we also operate a drift model, and this drift model helps us to predict the arrivals of sargassum and the stranding of sargassum. So the satellite sensors are, as I said, from Copernicus Sentinel satellites or NOAA satellites. And for the drift model, we are also using some data from Copernicus, from the CMEMS platform, to valorize again all this European data. Next slide, please. And so the best now to show you what is the SAM tool was to present you a demonstration. So it will not be a demonstration, but I have a couple of slides that I will screenshot of the system. So if you go to the next slide, please, Audrey. So when you log in on the system, so it's really, the web page is really similar to Lithoscope that you've just seen before. It's based on CLS background in software. So when you logging onto the system, you have the latest situation of the sargassum detection using the satellite sensors. So on the screen here, you can see on your area of interest. So you have the latest detection here in yellow from the Sentinel-3 data. Now, if you go to the next slide. So when you zoom in on these detections, so you can see on the right image that in yellow you have the results of the sargassum detected with the satellite Sentinel-3. This gives you an information with the 300 meters resolution pixel. And when you have on the left, nearly the same information, but with a high resolution sensor, so Sentinel-2 sensors. And these satellites actually allows you to detect sargassum at 20 meters resolution. So here you have the same, for once, you have the same mats, sargassum mats detected with 2 different satellites, but with a different resolution. But it can also happen that when you have too much cloud, when the satellite passes, you cannot see any sargassum. So that's why we are also using 6 satellite sensors to increase our chance to actually detect the sargassum, because when you have cloud, you cannot see the sargassum. Next slide, please. So once you have detected the sargassum, so now I am zooming in on one particular area for the demonstration, which is the Barbados. So in red, you have the sargassum that had been detected on the 19th of September. And we run on a daily basis the drift model. So if you go on the next slide, please. Oops, sorry, no, next slide. Yes. So from the latest detection, so here you see in black the sargassum detected on the 19th. So we run this drift model and we display the results on the website. So you can see in white the estimated trajectory of the sargassum and their estimated position on the date of the 21st of September, which is today. So you can see that from what we have detected on the 19th, we estimate that part of the sargassum are still drifting. They are represented in yellow here. And some of the sargassum have actually landed on Barbados, which is what you can see in red. So all this information is provided to the users, and they help this information to, they use this information to prepare any collection or mitigation plans. And on the next slide, please. So now if I zoom out a little bit, so to show you also the area that we cover with the system, we are also able to actually detect sargassum in the whole Atlantic area. And this was something that we have added thanks to the eShape project to expand the detection to the West African coast. And here you can see that actually sargassum at this season of the year, this season in the year, are actually drifting in the central Atlantic. And if you go to the next slide, I zoom in on the West African coast. And here you can see that at the moment, so from September to actually December, we can see sargassum on the west part of on the West African coast. Okay, yeah, next slide, please. Okay, so this was just to show you a little bit what kind of information we can find from the website. Now this is a feedback that I wanted to share with you because recently we've done with a particular user, we have helped them to go and find sargassum at sea. So providing the information that you see on the left, so with the detection of the sargassum and some estimation of the length of the sargassum map, providing also information on the drift, expected drift, and on the right side you can see the image of the sargassum that they actually found on this specific area, a specific point. So this is a very good information for us in two ways. So first, to see that our system is working, but also it really provides us some in situ information of what is actually what is the reality of the sargassum mats from what we can see on the satellite sensors. Now just 2 slides to conclude. So next slide, please. So now if I focus on the eShape results, which are still ongoing today. So as I mentioned, we are working with the CERMES as an ambassador user, so who is using our data to provide their own bulletin. Thanks to this discussion, we have upscaled the solution to regional level to include the West African coast. We have also continued our work and improving our algorithm on the satellite detection to remove some artifacts that were occurring close to the shores. We've computed also a 1-year analysis of Sentinel-3 data, and this data will be available. This data will be shared with the scientific community. And finally, the CMS also, as I mentioned, is producing. So it's a co-production, or they are producing their own bulletin based on our data. Next slide, last slide. So what is next now? Just to summarize a little bit the feedback from this project. So we had a strong involvement of the users in the co-design of this system. So from 20 users at the beginning of the experiment, we have more than 60 now at the end of the experiment, and even more through our ambassador for the co-production of the final bulletin. This is a solution that is scaled at the Atlantic regional level, so from Gulf of Mexico to West Africa. It is valorizing the Earth observation satellite data from Copernicus programs and also NOAA programs. And finally, we want to share knowledge, and part of the data that we are producing is shared with the community through some publication, but also through the Sargassum Hub that we are putting this in place with the GeoBlue Planet. And just a last thing, to be able to continue sharing this knowledge and sharing the part of the data, we also need to sustain our operational system, which allows us to calculate all this data on a daily basis. And this is the next slide. And this is just the end of my presentation. So I'm happy to answer any question you had. Thank you.
Thank you, Marion. So just one question. So your solution, the SAM2 contributes to EuroGEO via the Sargassum Hub. Is that correct? Or they?
Yeah, so what we have been developing in eShape. See, it's really on a reanalysis of Sargassum data, and this data is very valuable for scientists that want to understand and continue to understand the process and validate the hypothesis of the circulation of Sargassum.
Okay. We have another question. Have you ever tested the SAM2 at the Strait of Gibraltar, Gulf of Cadiz?
The area covered is we detect Sargassum from so 5 degrees less south of the equator and up to 30 degrees north. So all this area in the Atlantic is covered. So I did not go specifically on this area, but we could have a look at this. Although usually, yeah, well, on this map that Audrey is showing, you have the yellow region is really where you find Sargassum most of the time during the year.
Okay, thank you, Marion. I think we have no other questions. Thank you for your presentation.
Thank you.
So next up is Brian Jackson. Are you online? Yes. Okay, so Brian Jackson from Water Technology in Australia, who will be presenting the H2020 funded project WaterSense, making sense of the water value chain in Australia. I invite you to share your screen.
Thank you very much. Is that displaying?
Yes, it's displaying.
Great. Yeah, thank you very much for the opportunity. Coming to you from Australia. So I'll talk to you about the WaterSense project, which is a 3-year project, and we're now most of the way through the 2nd year of those 3 years for WaterSense in Australia. And if you want to follow us, you can see the website details, watersense.com.au, and the LinkedIn page, Project WaterSense, and the Twitter account, Make WaterSense. So WaterSense is a H2020 funded project. It is trying to change the slides now. Not sure why it's not letting me change slides. There we go. So it's a consortium of companies, mostly sort of research focused companies in Europe and Australia. So eLeaf in the Netherlands, who are the main lead of the project, Hydrologic Research as well in the Netherlands, who are the developers of HydroNet, the platform through which most of the products are made available. Water Technology ourselves, a water flood modeling consulting engineering firm in Australia. University of Sydney, our main research partner, Hydro and Meteor in Germany, weather experts and rainfall experts, Hidromod in Portugal, who are also a modeling company, and Mark Nuert, who is with us from HCP International in the Netherlands as well. So the main mechanism of this project, oh, sorry, jumping the gun here. Yeah, WaterSense is contributing to EuroGEO, and we're part of the GEOSS initiative, and we are planning contributions in the third year to AfriGEO, EmeryGEO, and EuroGEO as well. Back to the project. So WaterSense is strongly focused on a co-creation approach with a double loop learning process to the market. A large part of the first year of WaterSense was understanding the user needs and the market analysis in Australia around water management and water resources. And a lot of effort went into understanding that and identifying priority needs and gaps that remote sensing and the Copernicus datasets can actually help to help with. And through that process, we have developed a number of demonstration applications, which I'll show to you in the next slide. And the process is through those demonstrations, we will use our technical work packages to actually develop the algorithms that are required and the application, and make a demonstration with a demonstration partner. And that demonstration partner then uses that application in conjunction with us for a period of 1 year, through which we further develop through their feedback on that into a final application that's market ready. The application that we'll be talking to that's available already is the irrigated water use determination application, and our partner, demonstration partner, is the New South Wales Government Department of Planning, Industry and Environment. So I'm only going to be talking today about the water use monitoring and auditing service, which is one of the 4 main services that we have prioritized WaterSense to after the user needs survey. And in that water use monitoring and auditing services, the main application that we have already demonstrated and are busy demonstrating is the irrigated water use determination and the comparison of that with authorized and metered water use. But we also have a number of other modules that we are developing in that service as well at the moment. And they're listed there just for information afterwards. So the water use monitoring and auditing service is a satellite-based compliance check using the ET-Look and HSP algorithms mostly, which I'll go through quickly. It basically calculates the actual crop evapotranspiration due to irrigation and across an entire catchment at field level, and compares that to the authorized or allowed or licensed water use. The main idea of this is easy identification of big water users and water efficiency, and also compliance monitoring and enforcement assistance for planning, further identification or further detailed work that might be required for possible unlawful water users, for example. It's not to be used as a tool for direct enforcement, just an indicator to help identify where further work might be required. So at the moment, the demonstration is in the Namoi Basin, or the Namoi catchment of the Murray-Darling Basin, which I hope that everybody knows is the largest basin in Australia. So on the top left there, you can see Australia and the Murray-Darling Basin. And then zooming in further, the Namoi is a fairly significantly large catchment in that basin. So that's our demonstration area. And within the Namoi, if I zoom in now, we are demonstrating this application at the lower 250 meter resolution across the entire catchment. But within that blue box, which is one of the satellite sentinel tiles, we are demonstrating it at a higher resolution using 10 meter remote sensing data. So through the co-creation, we actually have work to do ourselves, but our demonstration partners, the DPIE, also have had research to do as well. So on the left-hand side, I'll go through the whole process of determining irrigated water use using ET-Look and hydrologically similar pixel methods. And on the right-hand side is the DPIE, who have had to develop a lot clustering algorithm, which I'll also explain a little bit more detail of what that is. So to be able to compare remotely sensed-based irrigated water use at a field level to actual authorized water use in Australia is a very complicated process, because Australia has a very complicated water use authorization process. You cannot compare a license to a field or to a pump station or to an individual work. So in this diagram, you're seeing the river on the left and all the pump stations that are linked to various works, which could be a field or another pump station or a dam. And each of those works are within a certain lot or property or farm. Now, if you look on the right-hand side or the top right-hand side, there are access licenses and work authorities. And those are all actually interlinked to various lots and various works. And you cannot compare one farm to a single license. So the only way you can compare what we are picking up on every field is to somehow cluster the lots or the farms that can be linked to a number of access licenses. And this is an example where the entire orange area making up of 5 different lots or different farms can be linked to 2 work authorities and 2 access, or 3 work authorities and 3 access licenses. So we can compare the satellite information to the authorized water use at a cluster level. So we've now produced an application that is providing the water use information at a field level and a lot level, but also comparing that to authorized use at a cluster level that the DPIE, our demonstration partner, have now developed. So just quickly, I'm not an expert and I'm not the modeler, but the ETLOOK is a remote sensing based evapotranspiration model, energy balance model, and using the Penman-Monteith equations, calculating the physical processes. It's a progression of the original Seabell algorithm that was developed in the Netherlands and is now coupled to a automated processing facility that enables it to be utilized across an entire area and not only calibrated per image, but calibrated per area. So this is what enables us to now information across an entire catchment or even an entire continent if required. Because that processing facility can process those images every day and produce the outputs automatically once it's set up. The second actual model that we use is the hydrologically similar pixel method. So the first model, ETLOOK, is just calculating actual evapotranspiration on a pixel. The second process is actually now calculating what are known as or identifying the closest natural pixels. So I'm not going to go through all the 10 steps, but basically what it is doing is identifying around the irrigated pixel that's identified natural pixels that are very similar, have similar static data, so similar aspect, gradient, wetness index, root depth, and it compares the 50 closest natural pixels to the irrigated pixel and calculates the average evapotranspiration of those natural pixels around the irrigated pixel area. The average natural evapotranspiration and the irrigated and the evaporation of the irrigated pixel, the difference between those two is basically considered to be applied irrigation. It's more complicated than that because there's also groundwater impacts that are used, and there's a lot of calibration and validation that's going on. But in essence, you're comparing evapotranspiration from natural to irrigated, and the difference is irrigated water use. That is then aggregated to the fields that we have from the land cover classification provided. And you then get information on irrigated water use for each field that can then be compared to the allocated water use per cluster. It is now set up in the HydroNet application for our demonstration partner. And these are just some screenshots of how it looks at the moment. So this is irrigated water use in megaliters on the left for all of the clusters across the Namoy catchment, and for megaliters per hectare irrigated application rate on the right for all of the clusters. You can zoom in to the clusters and to the fields, and you can click on those and you can get the information and charts of the use against the allocated use. So on the left-hand side here is a difference dashboard, which is comparing the estimated irrigated use from remote sensing to the observed allocated water use, so the metered water use that the department has. And obviously, if it's red, it's implying that they have used more than they've been allocated for the year. And on the right, examples of fields or clusters clicked on, comparing in the light blue line is the irrigated water use estimated from our remote sensing data sources, and the other lines are the metered water use from groundwater regulated and unregulated systems that they have. Black line being the sum of those. In some cases, you can see it's quite a good correlation. In other cases, it's less good. And now my last slide will basically talk about our current understanding about why there are quite some differences in some cases. Just the last one is the water availability balance, which is just comparing the actual use to the allocation and how much of the allocation may be left in a particular hydrological year. So some quick results. This is just a particular field at medium resolution. You can see it doesn't cover the field very well at medium resolution. At higher resolution, we've got a much better coverage of the data, but we don't necessarily get a much better product out of that higher resolution because it comes at a not nearly as often in time. So the temporal scale is a lot lower, even though the spatial resolution is higher. So there's the benefit of higher temporal resolution versus higher spatial resolution. It's still a bit of a process we are trying to understand which is better. So one of the issues that we have is that we are actually comparing what we are picking up on the field with remote sensing to a water meter that is actually often very far away in the river system or at a borehole abstraction. And a lot of the farmers in this area actually pump their water into dams or on-farm dams, and they do that for 3 months in a year without even using it on their fields, and they apply it to the field at a very different time of year to when they're pumping it out of the resource. So on a month-to-month basis, you can't actually compare the field to the meter because they are actually measuring different things. So this can be a big source of error. And it's the main source of error. And one of the products we are looking at now with WaterSense that we do not have results to show you yet, but is using remote sensing to try and improve the estimation of volume change in these farm dams and improving the accuracy of dam volume change. And having that in the balance will enable us to better compare the metered use against the satellite use. There are the other usual sources of error are water losses, distance from the meter to the farm, and the transmission losses, the type of irrigation and the efficiency, and the accuracy of the land use classification. So the land use classification, the application requires a land use classification to be in place because we do this within the irrigated land use mask that is coming out of the land use classification. Through WaterSense in the third year, we are also exploring an automated irrigated water use land use detection process that will enable us to actually detect irrigated land use in season, because unfortunately the land use classification from the previous year is often not what's being irrigated in the following year. So because people are rotating the irrigated water areas quite frequently in Australia, and using a land use classification from previous years is not covering all of the land use that is irrigated in the current year. So that's a further development that will be in place in the third year. This is just a demonstration of how the dam, so on the top and on the bottom are two dams, and you can see the bottom one is a good example where the dam is full on the left-hand side at the bottom and is emptied until about November 2017, and then fills up again quite quickly. Now that sort of couple of week period between being almost empty and full up is when the user would have pumped from the river system and the observed meter would have shown water use, not when our satellite information would have been picking up application to the field, which would be during these drawdown periods of the dam actually. So there's almost a disconnect completely between the water meter at the resource and the satellite field detection. But with this information, we should be able to compare them more impressively. Yep. If you'd like to connect with us, there's our contact details globally and for Australia. My last point I'd like to add is that the current focus of WaterSense is Australia because we're new signatories to the Copernicus Agreement, but it is a global project that will also be moving its focus to the Netherlands and South Africa as a second step, and then further afield as a third step. But currently the main focus being Australia. Thank you.
Thank you, Brian, for your presentation. We have one question. How did you identify your users and how did you engage with them? How did you analyze their user needs and address the co-design?
Yes, well, that's partly why water technology, myself, or our company is involved. It was one of our main roles in the project. So, because we have quite a good knowledge of the all of the users and the water sector in Australia. So the process was quite complicated, actually. Probably take a little while to explain. And it was definitely
1 minute.
It was very much, I have to say, it was very much impacted by COVID, because we started out with a number of the regional conferences that we went to. We identified users from there. We sent out messages to all of our contacts that we have, and we set up a whole lot of workshops with users. And through those workshops, word of mouth started going. We had further workshops, so it was a whole lot of different workshops where we had discussions, a number of different discussions with different users about their needs and what the challenges are and what the gaps are. And with all of the stakeholders we managed to actually get to, we've got a whole list of stakeholders in each state and at different levels, from local to state to federal stakeholders, and who the contacts. So we've got a whole contact database that we've developed out of that. And the priority ones were, we had workshops with them, and we developed a report on the user needs of each of those different stakeholders. And that then fed into a final report, which was a priority, where everyone was saying we have this need and these are therefore the priorities for further research.
Okay. Thank you. Thank you for your presentation and for your response. I think somebody's mic is on. Okay, we will go to our last presentation by Alexia Tsuni, who is from the National Observatory of Athens in Greece and will also be representing the Beyond Center. And she'll be speaking about the Flood Hub operational service supporting civil protection in flood early warning and monitoring.
Hello, everyone. Hello, and thank you for inviting us and for attending. Can you see my screen now?
Yes, we can see your screen.
Okay, great. So we will present here with slides and demo videos our operational Flood Hub system, which has been developed by our Beyond Center of Earth Observation Research and Satellite Remote Sensing in the framework of the EuroGEO Disaster Resilience Action Group. It's a user uptake, is supported by FPCAP, the Caroline Herschel Framework Partnership Agreement on Copernicus user uptake. So let's see a bit the challenge. Floods, as you can see in this recently published infographics, was the most frequent type of disaster by far in 2020. And what is more, flood occurrence was significantly increased in 2020 compared to the 2019 annual average. Furthermore, the number of deaths due to flood was the second largest in 2020, and the only one which was increased in 2020 compared to the 2019 annual average. Coming to Greece, we had an extreme flood event in 2017, which affected both the urban and suburban area of Mandra, close to Athens, with landslides, extensive €1 million damages to properties and infrastructure, and 24 recorded fatalities, rendering it the deadliest flood in Greece in the last 40 years. Therefore, we decided to develop our Flood Hub system first for this river basin, the Mandra River Basin. And what's the architecture of our system? It's an integrated near real-time flood monitoring and early warning system based on modeling, multi-source Earth observation, and crowdsourced data. This supports the decision makers in flood risk management, and it's built around a fully scalable and transferable modular architecture. As you can see in this image here, this allows the near-time ingestion and the simulation of hydrometeorological parameters, measured at 3 in situ telemetric hydrometeorological stations, satellite data, and crowdsourced data in a multi-source data fusion concept. These data are stored in a data cube, and we have this PostGIS RDBMS, which offers flexible environment for flood analysis and comparisons. So we take the most common hazard parameters out of this, the return period, the antecedent soil moisture conditions, and the rainfall duration. We give every 5 to 15 minutes to all the relevant authorities on 3 levels: the municipality, the region, and the Civil Protection General Secretariat, a reliable operational awareness picture of the crisis. And this offers increased reliability through a continuous validation and optimization of results, automation in assimilating flood modeling in real time, and computational efficiency, flexibility, transferability, and the speed to meet rapid awareness during the crisis. So for the needs of our operational flood hub system, we first installed 3 state-of-the-art telemetric hydrometeorological stations in 3 critical positions in the Madra River Basin. This is the platform, our web platform, with the 3 stations, which you can see here in blue, collecting and transmitting data in near real time in order to cover the operational needs. Thus, the Flood Hub service can first of all provide to all the relevant operational authorities measurements of these 10 parameters that we can see here. And based on these, we calculate automatically the 5-day antecedent rainfall in order to estimate the category of the CN, the curve number, which relates to the antecedent soil moisture conditions. So to have an input in our model if it's a dry, average, or wet soil moisture conditions. Now we'll show the first demo video of this platform, the MeteoView 2 web platform, which provides the real-time data for the 3 telemetric hydrometeorological stations. This here you can see the first station. It's installed upstream in one stream, the Sure stream, in the mountainous area in order to provide reliable rainfall data and early warning. This station operates with solar panels, so it provides data every 15 minutes. The second one, which we can see here, it's installed upstream of the new diversion work, anti-flood work after the flood. It was constructed of Santa Caterini stream. This now stream is diverted towards the Sure stream. And again, this has a solar panel and provides data every 15 minutes. And the third station, it's installed at the entrance of Madra, downstream of the conjunction of these 2 streams, which operates with electric power provided by the Attica region, and that's why we can have every 5 minutes data. So we can see here the different parameters that we can choose the time period. We have also the possibility of a comparison view among the various parameters. Here you can see, for example, the water level and the rainfall in the chart. And we have also the possibility to have live images from the camera of this central station so that we can have a visual recognition and a check. And we have also equipped this with a water level scale. So at the same time, we can compare the measurements of the same parameter between the different stations. Here, for example, we have chosen the rainfall, and we can compare it between the 2 different stations to see. You can see more rainfall, of course, on the upstream parts, and where's the mountain, and less rainfall downstream. These measurements are received in real time through an API and feed our flood monitoring and early warning system, which we'll present in the following demo. And here we can also have a definition of some alerts, like we do here. We define some alerts, such as if the water level exceeds some limit, we send an SMS to registered users. Here you can see some of them, like the fire brigade, the civil protection, so they have an alarm on their mobile phone. Now let's see the second demo, the integrated Flat Hub system. We give access to all the certified and trained users of the civil protection, the fire brigade, the municipality, but also the association of volunteers. So they log in like this from our website, and we provide through this Flat Hub platform a first assessment of the flooded areas based on these 3 meteorological stations, and that we can see here on the purple dots, and with the modeling that we have already run, the pre-defined scenarios. Now we can see here the area of interest. We can zoom to the urban area of Mandra, and we can simulate an extreme rainfall scenario so that we can see how it will develop and the evolution of the flood. Here on the left panel, you can see the measurement of the water depth and the location in this location of the selected station. So we collect and analyze the near real-time measurement of the water depth and extent in order to choose the exact flood scenario from all those that we have pre-run, which best fits to the in-situ measurements. This flood extent assessment is automatically updated every 5 to 15 minutes with the new in-situ measurements by the telemetric stations. And you can see, for example, now on the left that it's increasing the water depth in the panel on the left, and gradually on the map on the right, there is a flood which is increasing constantly. The Flat Hub system presents the best fit scenario, and its parameters are shown on the left, the main parameters like return period, rainfall duration, and the CN, the curve number. So you can see here is the increase of the water depth on the left panel and the evolution of the flood on the map on the right, with the respective update every time on the parameters of the left. So now we have, for example, a repeat period of 100 years. After the peak, of course, now it's, you see now it's 1,000 years, the best fit scenario, which represents this this reality. After that, the flood, of course, will decrease, and constantly the parameters on the left are updated. Of course, this is a fast motion video. The operational update is every 5 minutes, but okay, I didn't want to take more time on this. So this is how really it works, and this is the operational awareness system, and a picture that all the relevant authorities can have either on their mobile or on their tablet or on the operational center in their computers. So this is how they can monitor, and they can have fast decisions during the crisis, also on how to best manage the crisis and send around the aid and the first response mechanisms. Now, in addition to this, we have developed here, I don't know, do you see the next video? Okay, here is the model, the hydrologic and hydraulic modeling that we use, that we integrate in this system. This is the river basin with the 19 sub-basins that we have divided in order to reach more accuracy and higher resolution also in the CN numbers in each sub-basin. We use the rainfall IDF curve of Koutsougiannis and Balouchos. So we have a distribution according to the worst profile method, and we calculate the concentration time according to the Kirpich SCS method. We use the open access HEC HMS hydrological model, and we apply the CN method for extracting the excess from the gross rainfall, the unit hydrograph, and for propagating the surface runoff to the basin outlet. We run scenarios and we export flood hydrographs in an automated way for various combinations of return periods and rainfall duration for the 3 antecedent soil moisture condition categories. We use the open access hydraulic model HEC-RAS, and we execute the scenarios with a spatial resolution of 2 DMS at 10 meters based on the DEM provided by the National Cadastre and Mapping Service of Greece at 2 meters spatial resolution. And so we add the flow hydrographs for each stream of the hydrographic networks. And here we present the results for the combination of return periods 50, 100, 500, and 1000 years for the rainfall durations of 3, 6, and 9 hours. And for all the three antecedent moisture condition categories, dry, average, and wet. So you can see here in blue the flood, how it expands and how it increases with the worst scenarios. As a validation, we can see in this map an example of our flood hub system, the comparison between the actual and the simulated flood extent for this 2017 flood event, the extreme flood event that was the fatal one. In pink, we see the very high resolution satellite-based mapping, while in blue color, we see the simulated extent of the scenario with return period 1000 years, CN3 for wet conditions, and rainfall duration 6 hours. So you can see it's obvious for the accuracy of the flood extent estimation is very high. And here we see, we have zoomed the map to the urban area in the center of Mandra. In order to ensure the adequacy and reliability of our crowdsourcing data that we ingest in the flood hub system, we organize workshops for our certified users on how to use our web and mobile crowdsourcing platform. Here we can see photos of our trainings at the municipality of Mandra and at the operational center of the fire service in Athens. By the way, also we have received great media attention in addition to the scientific interest, as we can see here in the print screens of the news agencies. Therefore, the flood hub system is a useful tool in the hands of the relevant authorities and key stakeholders, supporting their decision-making process. It's in line with the requirements for the implementation of the EU Floods Directive, the Sendai Framework for Disaster Risk Reduction, the UN Sustainable Development Goals, as well as the GEOSS societal benefit areas. And to close with and to sum up, I will show you just the last short video as an example of our cooperation with the relevant stakeholders and the user uptake of our flood hub solution.
We can't hear the sound. Is that normal?
Sorry, no, there is a sound. Let me, maybe I have, yes, sorry, it's my mistake. Let me try again. Now?
Yeah, it's okay.
Okay, thank you.
Είναι τεράστια προσπάθεια που γίνεται, διότι είμαστε σε μια περιοχή που έχει πληγεί στο παρελθόν με τεράστια προβλήματα, τα οποία πιστεύω ότι είμαστε πολύ καλύτερα σήμερα και δεν θα ξανασυμβούν. Και η περιφέρεια Αττικής, να ξέρετε ότι για όλη την Αττική αγκαλιάζει αυτές τις προσπάθειες, συνεπικουρεί το έργο όλων των φορέων.
Έτσι λοιπόν είπαμε να φτιάξουμε ένα σύστημα το οποίο να δημιουργεί μια επιχειρησιακή εικόνα όσο γίνεται, με μια συχνότητα κάθε 5 λεπτά της ώρας, ώστε να έχει το κέντρο επιχειρήσεων μια εικόνα. Ανεξάρτητα από την εκτίμηση εκ των προτέρων, που είναι πάρα πολύ σημαντικό πράγμα, τι με περιμένει με βάση τα χαρακτηριστικά της περιοχής. Αυτή λοιπόν είναι η πλατφόρμα, η διαδικτυακή μας πλατφόρμα, στην οποία έχουμε τοποθετήσει, βλέπετε εδώ με μπλε, τους 3 σύγχρονους σταθμούς υδρομετεωρολογικούς τελευταίας τεχνολογίας. Ταυτόχρονα φτιάξαμε και μια πλατφόρμα η οποία δίνει με βάση αυτά τα στοιχεία, αλλά και στοιχεία τα οποία έρχονται από τους εθελοντές που πάνε σε πολύ κρίσιμα σημεία και μας δίνουν πληροφορία από τα πολύ συγκεκριμένα κρίσιμα σημεία όλο αυτό το τεράστιο δίνει που λέγεται Village Mappers. Κάποιες 2-3 πληροφορίες οι οποίες αυτόματα μπαίνουν όλα μαζί σε ένα σύστημα και φτιάχνουν μια επιχειρησιακή εικόνα για το τι συμβαίνει σε όλο το Δήμο. Εδώ λοιπόν βλέπουμε ότι δυναμικά αλλάζει η εικόνα της πλημμύρας και έχουμε ακριβέστερη αποτύπωση όσο πιο πολλά δεδομένα έχουμε. Περισσότερο να ευχαριστήσω το Αστεροσκοπείο Αθηνών για αυτή την πρωτοβουλία σε αυτό το κομμάτι του παζλ της ασφάλειας από τις πλημμύρες του Δήμου μας και θα έλεγα ότι αυτό το κομμάτι στο παζλ της ασφάλειας έχει μια ιδιαίτερη σημασία γιατί έχει προληπτικό χαρακτήρα. Πραγματικά έχει μια ιδιαίτερη επιστημονική μονάδα η οποία με την προσπάθειά της και με την επιστημονοσύνη της μας δημιουργεί μια ασφάλεια. Σας ευχαριστώ. Για μέση και εμείς, κύριε Δημάρχη, ευχαριστούμε πάρα πολύ. Ευχαριστούμε για όλη τη στήριξη που μας δίνετε. Να είστε καλά. Να είστε καλά. Ευχαριστούμε πολύ.
So on behalf of the Flat Hub team and all the other teams of the Beyond Center, I would like to thank you very much for your attention, and I remain at your availability for any questions you may have.
Thank you, Alexia. See, your mayor was very happy. Well, thank you all for taking the time to present today. We're going to have a break and join the plenary session at 11:45. At 11:40, we'll be automatically redirected to the plenary session. Otherwise, you can disconnect and reconnect. And then just one thing, all the presentations will be made available on the website. So could all the presenters just send your latest version of your presentations to Elwin? I think, Audrey, do we have anything else? Yeah. Oh, yeah. Could all the speakers, if you're available, please also assist the plenary session in case any questions, because at the plenary session, there'll be a summary of the different projects in each breakout session. So thank you, everybody. See you in 15 minutes at the plenary session. Have a nice day.